Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gil Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gil@eapen.info. My guest today is Professor Fran Bagenal, who is a professor of astrophysical and planetary sciences at the University of Colorado, Boulder, and a researcher in the fields of space plasmas and planetary magnetospheres. Her career spans involvement in the exploration of the outer solar system with NASA's Voyager, Galileo, New Horizons, and Juno missions. Welcome, Fran.
It's a pleasure to be here.
Thank you. Yeah, so I want to start with Pluto. You have a paper entitled Pluto's Interaction with its Space Environment, Solar Wind, Energetic Particles, and Dust. Pluto, I guess, cold and probably sad, having been demoted from planetary.
Wait a minute. Dwarf people are people. Dwarf planets are planets. Okay.
All right. But you know, a little bit of a demotion at the very least. But it is way out there, and it is sort of a strange world. So we sent a mission that you are intimately involved with, called New Horizons. Left the Earth around, I believe, 2015. Is that right?
No, I left Earth.
Oh, that is a
2006.
flyby. 2006.
It's
Okay.
a 9-year flight out there.
9-year
Long
flight.
time.
Yeah, hopefully it's not. It's first class.
Yes.
So 9-year flight, and so the flyby, the first flyby, I guess, was in 2015, and it is still around Pluto, or it is taken off from there?
No.
Okay.
We were moving too fast, and Pluto. We didn't have the fuel to go into orbit around Pluto, and Pluto is very small, so difficult to get captured. We went on straight past Pluto. It was just a 4-hour flyby, and then we went on to visit another Kuiper Belt object, and continuing to go out in the outer solar system.
Okay. Do we still have contact with Voyager 2?
Absolutely.
Oh,
Voyager 2, it's very interesting that we have to use the largest radio telescopes on the ground, radio receivers on the ground, the Deep Space Network. And they just did a 40-year upgrade or maintenance of the biggest telescope. So they had actually been out of communication with Voyager 2 for a few months, but I've heard they're back talking to Voyager 2 again. With the telescope out in California. So yes, this is pretty impressive that you need a 200-foot dish to 70-meter dish to communicate with these little spacecraft way the heck out there.
Yeah, but what's an amazing engineering accomplishment. Voyager 2, I don't have my timelines right. So when did Voyager 2 take off?
Voyager 2 and Voyager 1 were launched in September of 20 September of 1977. Okay, 1977.
And so I remember I was in Atlanta. I have faint memories in the early 90s. There was a lot of excitement. Was that then we got the first data?
So the first observations that Voyager took were at Jupiter in 1979, and then went on to Saturn, Uranus, and Neptune. And Voyager 2 flew past Neptune in September of 1989. Okay. So the 90s, probably what got you excited in the 90s was that we turned back after flying past Neptune to look at Earth. And so the picture, this was Carl Sagan's great idea, was to look back at what we called the blue dot. And it was a beautiful image that has the Earth and the other planets of the solar system. But this vision was of this small blue dot in space.
Right. Yeah, and so 1970s technology, and it keeps going, and it is an amazing thing to see, and we still have contact with it. New Horizons, much later, obviously, as you said, 2006. And this was a mission really targeting Pluto and its moons, right?
Correct.
And so what was sort of the objectives of the mission when we set off?
So when we flew past Neptune with Voyager in 1989, Alan Stern came to me. He was a student then at the University of Colorado. I was teaching my first class. And he said, after Pluto, what do we do after Voyager? Let's go to Pluto. We have to go to Pluto. And I was thinking, piddly little Pluto. Who cares about Pluto? Right. But what was interesting is he convinced me that it would be interesting to go to Pluto. But more importantly, we realized that soon after then, we started detecting lots of objects in the outer solar system around the orbit of Pluto, out at about 30 to 50 times the distance between the Earth and the Sun. So the Earth orbits at what we call 1 astronomical unit from the Sun. And these objects are 30 to 50 astronomical units. And these objects were, everybody started saying, what's going on out there? This is like an asteroid belt that is out there beyond the orbit of Neptune. And so we realized that Pluto was just the biggest of a whole family of objects.
Yeah. Is that what we call Kuiper Belt?
This is the Kuiper Belt. It was proposed by Gerald Kuiper, an astronomer, a Dutch astronomer living in America. And just as the Oort cloud is named after Oort, who was a Dutch astronomer living in America. And so there is this idea that we really, there's more to the solar system, and there's a key component of formation of the solar system that is being held by these objects out there. How did they get scattered out there? What process of solar system formation leads to a belt of icy objects in the outer solar system? So it developed much more scientific importance than just, oh, poor little Pluto, let's go look at poor little Pluto. It was much more about the science.
Right. Do we have an estimate of, clearly we cannot see everything in that region, but do we have a rough estimate of how many bodies we estimate to be in that arena?
Well, there are something on the order of a few thousand that are comparable in size to Pluto. Once you get down into, at some point you have to say, when does something get so small that it's not really a body, it's just a chunk of rock or a bit of dust, The smaller you go, the many more there are of them. But in comparable in order of magnitude, same sort of factor of 10 size of Pluto, there are a few thousand.
And that is, I would imagine that's unusual, right? So if you take a distribution of size, all those 100 bodies would be all the way to the right?
Well, okay, so indeed there tends to be a power law distribution, and you have fewer larger objects. So there's just, Pluto is the largest, and there's Eris and a couple of others that are comparable, and then you get smaller, and there's much more of those, and so on and so forth. So indeed, you get to the smaller objects, there's many more of them.
Yeah, and so Pluto is the largest. It is the king of the Kuiper Belt.
Just
about. So what is the second?
The second one is Eris,
Okay.
and I don't know the difference between them. I'm terribly sorry. But it's just slightly smaller, but they're comparable.
Okay.
I think they're both very interesting. They have, they seem to have different spectral signatures, maybe not the same. I don't think Eris has an atmosphere. There are all sorts of things that would be interesting to go look at these other Kuiper Belt objects and compare them. I think just like our asteroids, they're all very different, and it would be interesting to go and explore more of them.
And Pluto, interestingly, has number of moons as well, right?
Yes. This is really bizarre that just as we were launching this, we knew there was one large moon called Charon that was discovered back in the 70s, and it's actually not too desperately different from the size of Pluto, and they orbit each other, so it's like a double planet system, and around a point that's outside Pluto. And so we knew about those for a long time, but then just as we were about to launch the New Horizons mission to Pluto, we discovered with Hubble Space Telescope there were 4 small little objects that were orbiting Pluto. And so we now had 6 objects to go explore. And we flew through the system and took pictures of these small objects and found out, really strange, that they are spinning like crazy. So, they orbit around Pluto further than Charon, and they are these small chunks of ice that are spinning around. One of them spins 90 times in an orbit. So, our moon spins once in an orbit. So it's very strange to have this small object spinning around. So, there's a big question of these debris that were made during the formation of when Charon maybe collided with Pluto to get into its orbit where it is now. Was some of this debris left over? Why is it still spinning? All of these sort of things have got people going back to the drawing board to try and work out what's going on. How did this system form?
Yeah, so I want to get into the composition of Pluto, but before we get there, I remember, Fran, so this hypothesis of Planet 9, was it created by some sort of strange movement of bodies in the Kuiper Belt, or that's different?
So there's a question about whether there's another large object well beyond the Kuiper Belt that is sort of, what's the right word, that's pushing around the Kuiper Belt and making it orient in a certain way. And it hasn't been detected.
Yeah.
And there are now other theories that say, well, you can explain the orbits of the Kuiper Belt without needing a distant object. And so this is an open question. There could well be objects out there beyond large objects, planetary size objects out there beyond, but we don't necessarily need them, and it hasn't been detected. So it's actually worth telling this little story, if you don't mind.
Absolutely.
That when we started thinking about the Kuiper Belt and how it got to be there, it was around the same sort of time that astronomers were looking at other stars and finding objects around other stars. In particular, they were finding large objects, larger than Jupiter, which is 10 times the size of the Earth. And they were finding these big gas planets very close to the star. And everybody said, that doesn't make sense. You have to make gas giants, at least this was the theory of the time and still continues to be our current theory. You make gas giants by having a lot of ice balls, big snowballs. I mean, snowballs about 20 times the mass of the Earth, that form beyond the ice line, which is well beyond the asteroid belt, where ice could freeze to warm closer to the star where we are here. And so then you pull in hydrogen, of which there's abundance, large amount. It's the most abundant element in the universe. And so you make these big gas giants out near where Jupiter is right now. So what were these big Jupiters doing in close to the star? And so people began to come up with ideas of planet migration. That is, you could make a Jupiter out where Jupiter is now in our solar system, but somehow maybe there was extra gas left in the formation disk, which caused it to drag and then end up close to the star. So this got everybody thinking about migration of planets.
Right.
And so then around the same time, people realized that it's really hard to make Uranus and Neptune where they are right now, because they move so slowly out far away from the sun that they would be moving through the big disk of material from which the planets were formed too slowly. So then came an idea: what if you had Jupiter, Saturn, Uranus and Neptune all forming sort of pretty much where Jupiter and Saturn are now, in that region of the solar system, so 5 to 10 times the distance from the sun as the Earth, so 5 to 10 astronomical units. And then somehow they got into a resonance with Jupiter, and Jupiter sort of started kicking out Uranus and Neptune. And as Uranus and Neptune migrated out through the outer solar system, they scattered the icy objects that were in the outer solar system. Some of them were scattered in to form the water that would be delivered to the Earth to make our ocean. And some of them would be scattered out to make the Kuiper Belt. So this idea of planetary migration, which was sort of provoked by detection of stars around planets around other stars, got us thinking about formation of the Kuiper Belt, migration of Uranus and Neptune. And this now is our current, a major component of our ideas about formation of our solar system.
So it's migration away from the sun and Jupiter.
For the case of Uranus and Neptune, because what may have provoked that was a resonance, an orbital resonance with Jupiter that sort of kicked them out. On the other hand, if the dust and gases of the solar nebula from which the planets formed stayed a little longer, didn't get blown away by an active star or active sun, if you left that gas around, then you'd have a lot of drag and the planets would move inwards, right? So there's a combination of factors involved here, which would lead to different kinds of solar systems. And so that's why it's very interesting to look at all the different solar systems that we now have. There's several thousand of them out that we can see, and see that they have very different architectures. Our solar system is not necessarily typical.
Right. Yeah, and because we don't know the initial conditions, initial parameters, it's difficult to simulate that.
Right.
I would imagine. Right. Yeah. And so if Planet 9 were to exist, how far is the hypothesis?
Well, I think they're talking something like 300 astronomical units. So 300. That Pluto goes between 30 and 45. So many times further than Pluto. The Kuiper Belt, we don't know the edge of the Kuiper Belt, but it's probably somewhere around 50 astronomical units.
Yeah,
so much further out.
Clearly much further out. The reflectivity of that is going to be really, really low. So it'll be tough to find. I also heard something like some people are speculating that could be a small black hole.
Oh, sure. I have to admit that I'm a bit cynical, and people just pull in black holes. I know they exist. Yes, but I mean, they're somewhat used like magic, right? Magic.
Right.
Oh, let's bring in a black hole.
Yeah, when the math doesn't
Right.
work, we always tend to bring the black
Yeah.
hole, and that sort of magically
Yeah.
correct everything. So I want to go back to Pluto, and this is really a cold place, right? Something like 40 Kelvin.
Correct.
And so what do we know about the composition? Now, I would imagine with the New Horizons, we have a much better feel for what exactly is in there.
Indeed. So at those temperatures, not surprisingly, water ice acts like rock.
Yeah.
And nitrogen, the gas that we breathe here on Earth, the dominant gas that we breathe on Earth, 80% of our atmosphere, is solid. It's an ice.
Mm.
But it's an interesting ice in that it is actually denser than water ice at those temperatures. And so water ice actually floats in nitrogen ice.
Yeah.
Also, the nitrogen ice flows more easily. It's less viscous. It's more runny. Now, you maybe say, well, wait a minute, ice, runny, ice is solid. But of course, if you wait long enough, it will flow. That's what glaciers flow. And indeed, you can sort of think of nitrogen ice being a bit like silly putty. If you take silly putty and you make it into a ball in your hands and then put it on a table and wait 20 minutes, it will have flowed out onto the table. And so we know that a nitrogen ice acts like silly putty. And so the big heart shape that you see on Pluto that we discovered as the New Horizons was approaching Pluto, very warming to see the heart on the sun-facing side of Pluto.
It's not an ET leaving a message or anything
exactly.
like that.
I mean, anthropomorphic. we have to invent stuff. But anyway, it's a glacier, and it's a glacier of nitrogen ice. And we've now found out from New Horizons flying by that it's actually convecting. It's turning over the way a bowl of a pan of soup would be turning over on your stove. You heat it from below and you get these convection cells. And the same is happening on Pluto. This big glacier called Sputnik Planitia, obviously named after the Sputnik spacecraft launched by the Russians.
Yeah.
It is a big glacier with convecting ice. And so that's telling us that there's heat below, heating up this nitrogen ice and turning it over. And there are chunks of water ice that are floating in that nitrogen ice. So, wow, indeed, not what one would have expected.
Yeah. So what's the heat source? Is it nuclear?
Probably not much. There probably is very limited amounts of uranium and thorium and so on inside. It's probably mostly leftover heat from formation. So when you form a planet, you have chunks of stuff coming in, and that kinetic energy of chunks banging into each other generates heat. Gravitational potential energy, if you like, that is as stuff gets accumulating. And the question is, why hasn't it cooled off? And what we're learning, and I'm just hearing about this fairly recent meeting, there were some discussions that some of the materials in the lower ice layer may be sort of keeping the heat in, so they act as a form of insulation to keep the heat in, and that then is driving that leftover heat, if you like, is then driving this convection. Not that it takes a whole lot to do this, but it's interesting that we're learning that the exotic chemistry of these ices that could be sort of semi-organic ices that could have formed the Kuiper Belt objects can turn out to be a bit like polystyrene insulators.
Right. So if the water ice is floating on nitrogen ice, and nitrogen ice has viscous movement, would we see the geography changing? Is it at that scale?
Right. So what we see, the first thing we do when we look at planets is we look for craters, impact craters, because that tells us, is it a fresh surface or an old surface? If there are a lot of impact craters, you say, yeah, that surface has been around for a long time. It's got battered. So think of our moon, not had a lot of geology in quite a long time, and it's battered like heck all over, except for the mare, where there has been, and we can date those mare, volcanic activity that has sort of flattened it out, and a few less craters than other areas. When we look at Pluto, the Sputnik Planitia, for example, has no impact craters. So it's relatively fresh. And so we're talking a turnover time for the convection of on the order of 500,000 years or so, or million years, or, So that removes all the impact craters. And although we don't actually, in the same way you don't see an actual glacier moving, you can see the consequences of it.
Right. Yeah. So, but we won't pick up any measurable things in human time scale.
No.
Yeah. Okay.
Few places do you see geology on a human time scale.
Right. It would have been nice if it happened on Pluto.
Of course.
So the other interesting thing about the New Horizon mission I found very interesting, it has an instrument that is created by students at University of Colorado.
Very proud of this. Yeah. So here at the University of Colorado, we are very proud of not only having students do the grunge work, but we also give them the responsibility of being involved in designing, building, testing, and operating, not in fact just instruments on satellites, but whole satellites. We've had a student run things in Earth orbit, but we have this instrument on New Horizons, which is a dust detector, and what it counts the dust that it impacts. So as New Horizons was going out from Earth to Pluto and beyond, it had this dust detector pointed in its ram direction, its direction of motion, and any dust that it hit would be detected and counted by these little detectors that would then send the signal back to the Earth. Now, we're not talking huge amounts of dust out there. It's not like the Hollywood movies where, the actors in the Hollywood movies go through the asteroid belt and they're sort of fighting off left, right, center, anything that's coming towards them, right? No, it's not like that.
Yeah.
In fact, the dust detector would get maybe 3 or 4 hits a week. Okay. So.
Okay. And they're really small, right? Micrometers?
Yes.
Yeah.
So, space is empty, but the existence and counting of these dust is really important for us to think about the occasional collisions that happen in the outer solar system, particularly in the Kuiper Belt. And it'll be the dust detector that tells us when we get to the edge of the Kuiper Belt, because those dust detections will drop off drastically when we get to the edge of the Kuiper Belt. And so we're counting those dust particles as we go.
Yeah. Extremely interesting mission. We seem to have learned a lot from it. Well worth the investment. Do we have other ideas of of another mission back into that region?
Yeah, well, there's a lot of things being thought about and proposed and ideas going on. Some people want to go back to Pluto and go into orbit. Some people want to go to other objects and compare Pluto with the other large Kuiper objects. It's tough to do these missions. They cost $1 billion, which sounds a huge amount of money. But if you divide that by 350 million people in the US, that's a cafe latte per US person. And so, I think it's worth every penny, because I've given 50 public talks, 50 professional talks and 50 public talks. I added up the numbers the other day, and on Pluto. And I tell you, the kids just love Pluto. And if it gets them to do their math homework, oh my golly, it is worth every single penny of the money we spend. So there are people proposing at this. We proposed to do New Horizons. It was a competed mission. There are other competed missions that people are proposing, and we'll see. There'll be a competition where people write the proposals, and they'll be reviewed and evaluated. And at some point, NASA will make a selection and say, this is the next place we want to go.
Right. Excellent. Yeah, we will take a quick break, Fran. And when we come back, we'll talk about a bigger thing, Jupiter and its
Indeed.
moons. Thank you. This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com. So we are back. Fran, we've been talking about the New Horizons mission to Pluto. You have been equally involved with another mission to Jupiter, the Juno Mission. And you have a paper on this. So I was reading through. Juno Mission is revealing that our solar system's largest planet is a fantastic cyclone-festooned world with a strange interior. So again, from a timeline perspective, when was Juno launched, and when was the first flyby?
So Juno was launched in August of 2011. And it arrived at Jupiter on the 4th of July, 2016. And I think it was coincidence, but we all celebrated, of course.
So Jupiter is such an amazing thing. So before we get into the details of the planet, sometimes it's called a failed star, right? So it is not big enough. It doesn't have sufficient amount of hydrogen to really trigger that fusion reaction to become a star. What would have been the Earth's status if Jupiter were a little bigger and actually became a star?
Well, it would have to be about 20 times bigger, so it's an awful lot bigger.
Okay.
It's Jupiter is 320 times the mass of the Earth. Nearly 11 times the size of the Earth. So it's a really big planet, and the pressure at the center of Jupiter is 50 million times the pressure of the gas in our atmosphere. And that's a lot of pressure that compresses hydrogen and turns it into a liquid metal, a bit like mercury, very dense. But it's not enough to cause the fusion reactions that would make it a star, like the sun.
Okay.
So, if I don't know whether or not you can have an object like Earth survive in a double star system. I suspect the orbits are such that it would get kicked out. It would be hard to survive. Not so much the temperature, because of course
The gravitational.
It's more an issue of the gravity and the fact that you would have two bosses, if you like. You'd have the star and the Jupiter star fighting out,
right,
pulling you in multiple directions, and I think that would be unstable and would kick the planet out. Yeah.
Okay. Yeah. So it's almost like the right size for us. It also acts sort of like a vacuum cleaner out there, right? Protecting the Earth a little bit.
Well, I think that Jupiter in the earlier stages did a lot of scattering. So scattering of stuff out to the Kuiper belt, scattering of some stuff inwards to the inner solar system. But what it's done is it's scattered the leftover pieces of the solar system formation to the point where you now have fairly stable asteroid belt between Mars and Jupiter and a fairly stable Kuiper belt out beyond the orbit of Neptune. So in some ways, it does indeed suck up and get hit itself. So many people maybe remember the big impacts that happened in 1994 when we had Shoemaker Levy 9 bombarding Jupiter, broken up comet. It was pretty small, but I think Jupiter does indeed pull in some of the leftover junk that's lying around out there.
Right. So is Juno actually in orbit around Jupiter?
Indeed. Juno, this past Sunday, a couple of days ago, did its 30th orbit of Jupiter, flyby of Jupiter. So it has this orbit that is a 53-day orbit. And so it goes in very close to Jupiter, spends only 2 hours going from pole to pole, skimming over the clouds, and then it spends a long time, the rest of the 53 days, going all the way out to 100 times the radius of Jupiter, sending data back to the Earth, getting ready, and then we plan on next flyby, comes zooming in, does another flyby. So these long orbits are actually quite useful for planning and digesting the material of each flyby.
So it is designed that way so that we have that data transmission time.
Yeah, it's a little longer than we originally planned. But there was maybe some concerns about firing up the engines to shorten the orbit. But we ended up in what's turned out to be a very good one for this combination of having time to digest the material from one flyby before we get ready for the next one.
Right. And Jupiter is really big, right? Sometimes it's difficult to sort of imagine it. 11 times the diameter?
Yeah, about 11 times the size of the Earth, 320 times the mass of the Earth.
Yeah.
So yeah, it's a big object.
And it's mostly gas, right? Does it have a core of solid material?
Yeah, this is the big question that Juno was intended to set out. So as I said in the first half of our discussion, we have this theory that Jupiter formed as a huge snowball, 20 times the mass of the Earth, that formed out beyond the snow line, beyond the orbit of Mars. And then, because it was big and massive, it sucked in the hydrogen. And hydrogen being so abundant, there was a lot of it, and it sucked in a lot of it. So, 300 times the mass of the Earth of hydrogen. Yeah. And so we had this idea that we would go and test this idea of planetary formation by measuring the distribution of mass that's inside Jupiter. And we do that with a very clever technique. We watch the spacecraft and measure its motion using the Doppler shift of the radio signal. So just as the Doppler shift of a police radar measures the speed, the Doppler shift associated with a speeding car, we measure the Doppler shift of the speeding Juno, as it goes over Jupiter, and its perturbations of Juno's motion that we measure with these radio signals sent back to Earth that tell us what the distribution of mass is like inside Jupiter. And we've learned that indeed it does not have a simple, distinct core, just like the textbook draw. It's actually fuzzier boundaries, and that mass, that heavy elements that form the core are more mixed up with the hydrogen, extending further out, maybe 40 or so % of the radius instead of down in the inner 10% of the radius.
Okay. So if it had a solid core, I don't know the physics of it, but I would imagine it would have spun at a different rate than the gas, right? So would that create some sort of a magnetic
Yeah, I like your thinking. It's not quite the way it works. So you have a core inside, and even if it's a mushy core that spreads out,
right?
But the majority of the volume of Jupiter is out to say 5% of the outer radius, down to 40%, is liquid metallic hydrogen. So think of hydrogen as a gas where you have two protons together, each with an electron. So two protons, each with an electron, bound together in this molecule. Now, what happens when you increase the pressure a lot, so 1 million times or 2-3 million times the pressure of our atmosphere, you end up converting that hydrogen into separate protons and electrons. So the positive protons and negative electrons can move relative to each other. And this is liquid metallic hydrogen, which is electrically conducting. And so now you have a liquid conductor, you have some heat from the interior driving convection, and you have a bit of rotation, quite a lot of rotation in Jupiter's case, and you have the three essential ingredients of a dynamo, a magnetic dynamo. So in the Earth, we have liquid iron in the core of the Earth that is liquid, it's conducting, it has heat driving its convection, we have a bit of spin, we have a dynamo inside the Earth. And we know this is true also of Mercury, of Earth, of Jupiter, Saturn, Uranus, and Neptune. Those are the planets that all have magnetic fields, as well as one moon. Ganymede has its own dynamo. Okay.
Ganymede is Jupiter's moon.
So it's the largest moon in our solar system. There are 4 big moons, the moons detected by Galileo back in 1610, Io, Europa, Ganymede, and Callisto. And then there are, I think the last count was 79 moons of Jupiter. I think that's the right number. Up there, big number.
Right. And Europa, in comparison to Pluto, the biggest one is Ganymede, you said. So what is the size of that in comparison to Pluto?
Well, Europa is about the size of our moon, as is Europa. Sorry, as is Europa and Io, about the size of our moon. Ganymede's a bit bigger.
Yeah.
Callisto, sort of in between. Now, for Pluto, you could take Pluto and Charon, put them side by side, and they would be about the size of the moon. So Pluto is smaller.
Yeah.
Yeah.
Okay. Now, this red spot on Jupiter has been a fascination for forever.
Totally weird.
Totally weird. So with Juno, I think we have a much better look at that, right? Do we have a better feel for, it's sort of a hurricane or something that's going on for centuries, right?
Yeah.
Do we know more about it?
Well, it's really strange. Voyager got a really good view because Voyager could sort of stare at the Great Red Spot and watch it going around. What we've seen, and it's about twice the size of the Earth at the time of Voyager. Okay, so you could put 2 Earths side by side to give you the size of this big, large oval storm gyrating around, circulating every 6 days. We knew that from Voyager.
Yeah.
Now, what we've been doing with Juno, we only got one really close flyby over the top. And but we've had other observations what we've noticed, and ground-based observations of the Earth using telescopes and Hubble and so on, have told us is that the Great Red Spot has been shrinking. So instead of being twice the size of the Earth, it's now about 1.5 times the size of the Earth.
Oh, that's a big change.
Yeah. So over a period of 40 years, it's been getting smaller. And it will disappear at 2050 if it keeps going like this. So,
oh, wow. Yeah.
What's going on? And, will it break up? Will it just get bigger again? We don't know. We're going to have to keep watching it to find out.
Yeah. Can we, so given the data from Juno, can we now sort of model the dynamics of Jupiter?
Well, we're getting some very important information. And the way we do this is by looking at a different wavelengths. We use microwave detector, which is a really key measurement that tells us the amount of heat that's coming from the inside. But it also, as everyone knows, water absorbs microwaves, because that's how you heat a cup of tea. You put some water in a cup and you microwave, turn on the microwave, and the water absorbs the microwaves that are in your microwave oven. Now, if you have microwaves coming from the inside of a hot Jupiter, which is what is happening, you can measure as you fly over the amount of microwaves at different wavelengths, and it tells you the distribution of water in Jupiter's atmosphere. Okay. It also turns out that ammonia, which is a very important constituent of the atmosphere, also absorbs microwaves. And so by looking at different wavelengths, we can measure the distribution of ammonia and the distribution of water in the atmosphere of Jupiter. Right. And that has been really revealing. So we thought going in, and this is what I taught for 25 years in my intro astronomy classes, that Jupiter's atmosphere had a top layer of ammonia clouds. And we knew that because we could use astronomical techniques to say, yep, that's ammonia clouds at the top. And ammonia condenses at the lowest temperature at the top of the atmosphere. Then we said,
because of gravity.
Yes.
Just a quick question. So because of gravity, the atmosphere should be pretty close to the surface, right? Or does it extend?
Surface? What surface?
It doesn't have a surface.
It doesn't have a surface.
But it won't go too far out, right? Because it has a lot of gravity.
It has a lot of gravity.
Yeah.
And so it turns out that the gravity at the top of the clouds is not all that different than the gravity that we feel here walking on the surface of the Earth, maybe a couple of times more. So it's not huge. Because it's a big planet, right? So you've got a lot of mass, but you've also spread it. You're quite high up.
Right.
So it turns out that the scale height, the distribution of gas, is not too different in Jupiter's atmosphere than it is on the Earth. So the sort of separation between the clouds, it's a bit larger than Earth, but it's sort of more or less the same sort of idea. You have layers, but unlike Earth, where you have one layer of water clouds and then you have a surface, at Jupiter, you have a layer of ammonia clouds at the top.
Right.
Under that, you have a layer of this mixture of ammonia and sulfur, ammonia hydrosulfide, which is sort of probably is one of the contributions of the redness of the atmosphere. And then below that is the water clouds. And that's the sort of view we've had, these three distinct layers of clouds at Jupiter. Now, what we're finding with Juno is that indeed it's much more complicated. There's a lot more deep convection going from below the water clouds up through the water clouds, ammonia clouds up. And so there's more mixing. Yet again, when you look closer, things get fuzzier. And so there's not simple distinct layers. There's more of a mixing of the atmosphere and the convection, mixing of water of ammonia. And you end up making these huge hail balls that are, we call them mush balls, which are a mixture of ammonia and ice. which is really bizarre. But they're sort of the size, we think, probably of a softball, something like that, or large cricket ball, if you like. And these fall then down because as they get bigger and bigger, they'll begin to fall down, just as the hailstones do here on Earth. And then they go deeper. So you got it's a much more mixed up atmosphere that extends quite a long way down into Jupiter than we thought.
And it's fundamentally driven by solar energy?
No, not in. That's excellent question. No, turns out that Jupiter emits 2.5 times more energy than it receives from the sun. So this is the heat that's deep inside, heat of formation of this big 320 times the mass of the Earth object. That primordial heat is what drives the convection for the dynamo, but also what drives most of the convection of the atmosphere. And so it's less driven by sunlight, more driven by internal heat.
Okay. I want to quickly talk about Europa a little bit because of this interest of possible life there. Do we know anything more from the Juno mission?
Juno does not go very close to Europa. We've put in an application to extend our mission. Well, our prime mission ends next year, and we put in an application to NASA to have it extended for another 5 years, which will give us an opportunity to fly closer to as the orbit evolves, as we get closer to the moons, including Europa, and we will get a closer view. And it will allow us to get some sense. Maybe the microwaves will help us to find out. So the key things about Europa is that the Galileo mission to Jupiter revealed a couple of things. One thing is that it showed us that as we flew by, there was a perturbation in the magnetic field that we measured, Jupiter's magnetic field, that told us that there are electrical currents that are flowing deep inside Europa, most likely in a liquid ocean underneath the ice layers. So the images suggested there were cracks, places where some sort of brown gunky stuff seems to be coming up and covering the surface, places where there are cracks and dimples, places that look like icebergs and so on and so forth. But that ice is really thick. We think the ice is somewhere between 10 and 20 kilometers in thickness. And then under that, we have a huge ocean, 3 times the amount of water than in the Earth's ocean. But it's quite deep down there. But there is heating, and we think there's tidal heating. Resonances between Io, Europa, and Ganymede drives the volcanism on Io, just completely bonkers volcanism on Io. But the same tidal heating heats up Europa and could be driving volcanic vents underneath the ocean that could be bringing nutrients to a warm water environment, just like there are in the Earth. We have these black smokers, these volcanic vents deep in the ocean, and there are some ideas that is where life could have formed on the Earth. And so there could well be in the ocean of Europa some forms of life. We have no idea. Could it be charismatic megafauna like whales? Or is it, or is it just bugs? We don't know. Is that brown stuff whale poop, or is that brown stuff bugs? I mean, algae. Whatever it is, it'll be very interesting because it would be a life form that evolved separately, probably separately from the Earth, and it would be fascinating to find out what that sort of life is. And so there is a NASA mission that will go to Europa. It's not launched yet. It should be launched in a few years. And it will go to Jupiter, go into orbit around Jupiter, and multiple flybys, say 40 flybys of Europa, and make detailed measurements and give us a good clue about the composition, the structures, maybe some sense of the thickness of the ice. And then we hope later that'll tell us, where do we go to send a lander to scratch and sniff the surface and tell us what the brown gunk really is.
Right. Yeah. So in conclusion, Fran, if you look forward 5-10 years and you want to allocate whatever limited resources that the world wants to put into these types of missions, going out to planets in the outer parts of solar system, how would you allocate that? Just very approximately, what would be sort of your first and second targets?
Well, this is my own personal preference. I think the first priority should be Uranus or Neptune. Neptune is much harder than Uranus. So let's go back to Uranus. Voyager just did flybys of Uranus and Neptune and gave us one glimpse of these two outer gas giant planets. And they're very different from Jupiter and Saturn. They have a lot of more water. They have methane and ammonia and so on and so forth. It'd be very interesting to see what they're like inside. Uranus is tipped on its side, so it looks like it probably had a big impact fairly late in its life. How strange. It has a very weird magnetic field. So for me, a top priority would be to go back to Uranus. We'll see. And indeed, there's I'm involved in a survey of what do we do for the next decade in planetary systems. But I also want to mention something else, which is to go to Venus. Venus is in the inner solar system. It's our neighboring planet, same size as the Earth, basically. And it has no magnetic field. So I don't have a vested interest in it. No money in this game. But
life, possibly.
Yeah, well, in the clouds, there was this idea that there could be life in the clouds. I find that very unlikely. More importantly, why does it have a runaway greenhouse? Why is it like a hot oven? In fact, a broiling oven on the surface, and a totally different atmosphere, totally different geology. Why is our neighboring planet so different? I think we really, really have to go and find out. And learn about runaway greenhouse before we do this to ourselves.
Right. Excellent. Yeah, this has been great, Fran. Thanks so much for spending time with me.
Pleasure.
And good luck with this, all these missions.
Good. Okay.
Thank you.
Thank you.
Bye.
Bye.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.